Good morning, students. Very good morning. Hope you people are enjoying your live sessions, YouTube live sessions. So, myself Puneet Kathuria, your physics faculty at Aakash. So, today's topic, what we'll be discussing is, as you can see it would be from Thermodynamics and KTG, that is Kinetic theory of gases. So, let's begin the today's session. Thermodynamics. So, what do you mean by thermodynamics? So, if you split this word into two parts, so thermo stands for heat and dynamic stands for flow of heat. So, it means in this unit, in this concept, we will be discussing the flow or the exchange of heat. So, that would be definitely between system and surrounding. So, you have two terms. System and surrounding. So, system, what do you mean by system? So, here system is basically a container or a closed chamber where you have some collection of gases, some collection of molecules of a particular gas. So, that collection of molecules of a gas, that is called system. So, depending on the boundary wall of the system, you can have varieties of system. That may be an open system that allows the exchange of the particles as well as energy, and that exchange is with the surrounding only. So, what do you mean by surrounding? So, whatever is in addition to system, what is outside the system, that all is considered or taken as your surrounding. So, if system is allowed to interact with the surrounding, then how the system can interact with the surrounding? So, that depends on the type of system we have. So, open system that allows the exchange of particles as well as energy with the surrounding. Then you have another category called closed system. So, where you have a boundary, so that does not allow exchange of the particles, but energy can be easily exchanged with the surrounding. Then you have an isolated system. Isolated in the sense it does not allow even the molecules or even the energy. So, that is called isolated system. Now, this surrounding and system, they are interacting to attain an equilibrium. Got it? So, first, before we get into the details how the system can interact with the surrounding, what are the different processes by which a system can interact with the surrounding. So, let us understand the very fundamental law of thermodynamics, Zeroth law. And what do you mean by Zeroth law? It says if two systems are in thermal equilibrium. Now, what do you mean by a word called thermal equilibrium? So, if you split this word thermal, so it's AL ending, that means it's basically an adjective ending, that is therm means energy, that is heat energy, temperature, AL is adjective ending pertaining to heat, pertaining to temperature. So, equilibrium. So, it says two bodies are said to be in thermal equilibrium if there is no exchange of heat between these two systems. So, it means they are in thermal equilibrium if they are at same temperatures. So, temperature defines the internal energy state of the system. So, if two systems are in thermal equilibrium, it means there is no net exchange of heat between these two systems, and that means these two are at same temperatures. So, that is the basic fundamental concept of your thermodynamics. So, now Zeroth law says if a system is in thermal equilibrium with, let us suppose, system B, and system B is in thermal equilibrium with system C, then A would also be in thermal equilibrium with C. That is Zeroth law. So if two systems are in thermal equilibrium with a third system separately, then they are in thermal equilibrium with each other also. So look at this. If system A is in thermal equilibrium with system B, also system B is in thermal equilibrium with system C, then A and C would also be in thermal equilibrium. That is zeroth law of thermodynamics. And you know, there is an interesting story about this word also, zeroth law. So what do you mean by zeroth law? Why it is called zeroth law? So we know the first law of thermodynamics that was established, then second law came into existence, that was also established, and more work was done in both these two laws. So these were the two established laws. But later on, this law came into existence. This law was defined. And you know, looking at the importance, this law is to do with the temperature of the system. And temperature is rather more fundamental, rather the basic fundamental concept, basic fundamental unit of your thermodynamics. So I mean, like the people or the scientists or the community, they had no choice. So they had to call this law, or they had to place this law rather before the first law and the second law. Though first law and second law were well established well before this law came into existence, but to keep the importance of this law intact, to keep the importance of temperature intact, so that this law was placed before the first law and named as zeroth law of thermodynamics. So this is the story behind the zeroth law, and this is the only exceptional law, I mean, like in whole of the physics world, that is defined as the zeroth law. So quite interesting. So yes, Ritu Gupta, Sanjana, Numesh, and then Darshan, they all have joined. Hi, how are you? Hope you people have understood whatever we have discussed till now. This is all a theoretical conceptual concept before we get into the numerical part of this. This is quite interesting chapter. So I hope we have understood the zeroth law, the story behind the zeroth law, then thermal equilibrium, what is the condition for the two bodies or for two systems to be in thermal equilibrium. So again, this is very important. If two bodies, two systems are at same temperature, then there is no net exchange of heat between these two systems, and that is they are in thermal equilibrium. So shall we move? Now, before again you get into the action oriented concept of your thermodynamics, let's understand some of the basic terminologies associated with this. So we have heat, we have internal energy, and we have work. So first we have internal energy. So what is this internal energy is? It is represented by U. Internal energy. A system has kinetic energy by virtue of temperature, potential energy, gravitational potential energy, this energy, that energy. So what system actually possesses, that is sum total of all these energies, that is called internal energy. So it is the sum of the molecular kinetic energies and potential energies in the frame of reference relative to which the center of mass of the system is at rest. So it is primarily the kinetic energy of the molecules. So let's suppose if you have a chamber, if you have a gas container, and that is in motion, that motion will not participate in defining the internal energy of the gaseous system. So this is internal energy purely possessed by this gaseous system, and that involves the kinetic energies as well as the potential energies of the molecules, where kinetic energy will contribute to a much bigger extent. So internal energy is sum total of all these whatever energies a system can have or can possess by virtue of any different concept of physics. So that is sum total of all, and this is the internal energy. Now internal energy is purely a function of temperature, absolute temperature I am talking about. Got it? So if your temperature increases, it means internal energy also increases. If temperature decreases, internal energy also decreases. And if there is no change in temperature, then there is no change in internal energy. Do we understand? One more important concept that is important, internal energy is basically a state function. It depends on the state of the thermodynamic system. Nothing to do with the path how that state is achieved. So it is independent of the path by which that state has been attained, but it depends purely on the state of the system, that is state function. Nothing to do with the path, it depends purely on the initial and the final position of the state. Got it? Very important for cyclic processes. So what do you mean by cyclic process? Just understand it in just one word or one line. So if a thermodynamic system follows any path but comes back to the same initial state in n number of steps or whatever path it follows, if the thermodynamic system is coming back to the same initial state, the initial and the final position are same, then that process, the thermodynamic process, would be defined as a cyclic process. And very important, for a cyclic process, there is no change in the internal energy, and this is very important fundamental concept for any thermodynamic cyclic process, because this is a state function. So if your thermodynamic system, after following a particular series of processes, if it is coming back, reaching back to the same initial state, then change in internal energy would be zero. There would be no change of internal energy. So any doubt from this part? So again, internal energy, here we are talking about internal energy. So एक system की पहचान होती है बच्चों internal energy. A system is defined by its internal energy. So we say a system is defined by its internal energy, U. Got it? Any doubt from this part? Anything you would like to ask? Yes, Ritu, Ranjana, anything? Sanjana, Ritu, anything you would like to ask? Darshan? Fine. So I think we people have understood the concept of internal energy. So let's sum up. Internal energy, it's a state function because it is basically to do with the state of a thermodynamic process. Got it? Then it is sum of all the kinetic energies, potential energies, or maybe all the small contributions. By whatever means a system can have energy, so all they contribute to define the internal energy of the system. Very important. So this is a state function. System is definitely defined by its internal energy. For a cyclic process, we have just understood, for a cyclic process, the change in internal energy would definitely be zero. As we can say, internal energy is a function of temperature, absolute temperature. It means with the increase in temperature, there is definitely increase in internal energy. With the decrease in temperature, there is a decrease in internal energy. And then for constant temperature, if there is no change in temperature. रामेश्वर, हाय रामेश्वर, हिंदी में पढ़ाओ. ठीक है बेटा, आई विल ट्राई, मैं कोशिश करता हूँ बीच बीच में. सो अगर हमारा टेम्परेचर चेंज नहीं होता है, चेंज इन इंटरनल एनर्जी वुड डेफिनेटली बी ज़ीरो. इसका मतलब अगर हमारा टेम्परेचर कांस्टेंट है, सिस्टम में कोई चेंज नहीं आ रहा इन टर्म्स ऑफ टेम्परेचर, उस सिस्टम के लिए हमारे इंटरनल एनर्जी में भी कोई चेंज नहीं होगा. आई होप रामेश्वर यू हैव अंडरस्टूड दिस. So let's move to work done. Now this is very important, work done. So to understand the work done, we have understood or we have defined it as, let's suppose you have a cylinder and this cylinder is fitted with a piston. So this is your piston and you have gas that is filled in this. So this is a gaseous system. So we know this gas exerts pressure on this, and if this cylinder moves, to a new position, it means if that gas, by putting this pressure, moves the piston outward, so it means that is work is done by the system. So here work done is pressure into small change in volume, and if it is happening at a very small rate, so we can define it as small work done as P delta V, and for the total work done definitely will integrate it from the initial state, initial volume to a final state volume, and this is the concept of pressure. Got it? So very important, अब हमारे लिए समझने वाली बात है बच्चों, डेल्टा V. Delta V is change in volume, so that means final volume minus initial volume. Got it? अगर ये डेल्टा V पॉजिटिव रहता है, इसका मतलब हमारा फाइनल वॉल्यूम बढ़ गया है, तो here we are talking about expansion stroke. इसका मतलब हमारी गैस एक्सपैंड कर रही है, पिस्टन बाहर की तरफ मूव कर रहा है, डेल्टा V पॉजिटिव है, और इस सिचुएशन में हम लोग वर्ड यूज करते हैं, दिस इज वर्क डन बाय द सिस्टम. सो अगर हमारा एक्सपेंशन स्ट्रोक है, मतलब हमारा सिस्टम काम कर रहा है, तो वर्क डन इज बाय द सिस्टम, और उसके लिए हम लोग पॉजिटिव कॉन्सेप्ट यूज करते हैं, वर्क डन इज पॉजिटिव. अगर हमारा डेल्टा V नेगेटिव रहता है, इसका मतलब फाइनल वॉल्यूम इनिशियल वॉल्यूम से छोटा है, उस केस में हमारा वर्क डन नेगेटिव रहेगा और हमारी गैस कॉम्प्रेस हुई है. सो दिस इज कॉम्प्रेशन. सो इट मीन्स यहाँ पर हम लोग बात करते हैं वर्क डन ऑन द सिस्टम की. सो दिस इज वेरी इंपॉर्टेंट, ये बहुत इंपॉर्टेंट है बच्चों. वर्क डन बाय द सिस्टम, वर्क डन ऑन द सिस्टम. सो हमने जो यहां पर कॉन्सेप्ट लिया है, दैट वी हैव अंडरस्टूड इट, व्हेन अ पिस्टन ऑफ अ सिलेंडर इज पुश्ड डाउन, डाउन मतलब वी आर टेकिंग इट आउटवर्ड, द वर्क डन बाय द गैस बाय द सिस्टम इज टेकन टू बी, वर्क डन इज taken to be negative. Push down means, sorry, this is push down, they are taking it as the other way, that is compression stroke. So this is push down means compression. So if cylinder means this piston is pushed down like this, so it means this is work done on the system, because here we are talking about the compression stroke. Got it or not? And when the gas expands, so it means it is work done by the system, that is work done by the gas, and that is taken as positive. I hope आप सब लोग इस पूरे कॉन्सेप्ट को समझ पाए हैं. तो नटशेल में वर्क डन का कॉन्सेप्ट हमारे लिए क्या डिफाइन कर रहा है? वर्क डन दो ही तरह से हो सकता है बच्चों, या तो वर्क डन बाय द गैस, बाय द गैस में गैस हमारी एक्सपैंड करती है, वॉल्यूम बढ़ता है, और वर्क डन ऑन द गैस दैट इज ऑन द सिस्टम, जिसमें हम लोग बाहर से इस गैस को प्रेशर लगाकर कंप्रेस कर रहे हैं, इसका मतलब दैट इज वर्क डन ऑन द गैस। तो जब भी वर्क डन ऑन द गैस रहेगा, इसका मतलब हम लोग कंप्रेशन की बात कर रहे हैं, वॉल्यूम कम हो रहा है और हमारा वर्क डन नेगेटिव है। लेकिन अगर हम लोग गैस को एक्सपैंड करवा रहे हैं और बाहर की तरफ हमारा वॉल्यूम फैल रहा है, तो दैट इज वर्क डन बाय द सिस्टम, और इस सिचुएशन में हमारा वर्क डन पॉजिटिव रहेगा। सो आई होप दिस इज व्हाट वी हैव अंडरस्टूड इट एज वर्क डन। अब आपने अपने गैस को किस तरह से एक्सपैंड करवाया है, यू मे फॉलो डिफरेंट रूट्स, डिफरेंट स्टेजेस, डिफरेंट थर्मोडायनेमिक प्रोसेसेस, डिफरेंट थर्मोडायनेमिक वेज। इट मीन्स ये उस रास्ते के ऊपर डिपेंड करेगा, हाउ यू हैव टेकन द सिस्टम, थ्रू व्हाट प्रोसेसेस, थ्रू व्हाट जर्नी योर सिस्टम हैज बीन टू। सो वो डिफाइन करेगा हमारा वर्क डन कैसा रहने वाला है। इसका मतलब दिस इज अ पाथ डिपेंडेंट फंक्शन। फंक्शन के लिए मैंने वर्ड यूज किया एफ एन। सो ये डिफाइन करता है कि हमारा वर्क डन स्टेट फंक्शन नहीं है, और वर्क डन बाय द सिस्टम हो चाहे वर्क डन ऑन द सिस्टम हो, वो इंटरनल एनर्जी को चेंज कर भी सकता है और इंटरनल एनर्जी को चेंज नहीं भी कर सकता। दैट डिपेंड्स ऑन द थर्मोडायनेमिक प्रोसेस, हम किस रास्ते से, किस तरीके से उस वर्क डन को किस वे से अटेन कर रहे हैं। सो दिस वर्क डन मे और मे नॉट चेंज योर इंटरनल एनर्जी। यू गॉट इट और नॉट। जब हम चेंज की बात करते हैं तो चेंज में प्लस और माइनस, मतलब इंक्रीज और डिक्रीज दोनों कवर होता है। एनी डाउट फ्रॉम दिस पार्ट? सो कब हमें वर्क डन पॉजिटिव लेना है साइन कन्वेंशन में, कब हमें वर्क डन नेगेटिव लेना है? वर्क डन बाय द सिस्टम क्या है? दैट इज पॉजिटिव, जब एक्सपैंड कर रहे हो। वर्क डन ऑन द सिस्टम क्या है? नेगेटिव, जब आप कॉम्प्रेस हो रहे हो। वर्क डन एक पाथ डिपेंडेंट फंक्शन है, ये स्टेट के ऊपर डिपेंड नहीं कर रहा, रादर जिस तरह से आप उस स्टेट को अटेन कर रहे हैं ये उसके ऊपर डिपेंड कर रहा है। सो दिस इज ऑल अबाउट द वर्क डन पाथ। एनीथिंग एल्स यू वुड लाइक टू कंफर्म फ्रॉम दिस पार्ट? कुछ भी पूछना चाहते हैं पूछ सकते हैं बच्चों। यस रितु, केशव, रामेश्वर। रामेश्वर, नाउ यू आर ओके विद दैट? अभी थोड़ा थोड़ा हम लोग हिंदी में बात कर पा रहे हैं, तो क्या आप समझ पा रहे हैं? गुड। नाउ consider the process on a system shown in the figure below. During the process the work done by the system. अब हमने जो कॉन्सेप्ट सीखा है उस कॉन्सेप्ट को एक बार समझने की कोशिश करते हैं। हमने बोला वर्क डन इज गिवन बाय P डेल्टा V। अब आप कह रहे हो वर्क डन बाय द सिस्टम। सो जब आप वर्क डन बाय द सिस्टम की बात करते हैं तो ये पॉजिटिव रहने वाला है। इसका मतलब हम एक्सपेंशन की बात कर रहे हैं। यहां तक तो क्लियर है। अब हमें यहां पर P और V का एक कर्व, एक ग्राफ गिवन है। इस सिचुएशन में आपको वर्क डन फाइंड आउट कैसे करना है। नाउ लेट्स गो बैक टू योर फंडामेंटल्स। जब आप लोगों ने बहुत सीखा था शुरू में, इसके लिए हमारी सीरीज़ भी है, हम लोगों ने स्पेशल सीरीज़ भी लॉन्च करी थी, ग्राफ की सीरीज़, तो उसमें भी आपको ये एक्सप्लेन किया गया है। अब आपको P डेल्टा V इस इंटीग्रल को सॉल्व करना है, और इस इंटीग्रल का फिजिकल मीनिंग क्या रहता है बच्चों? इस इंटीग्रल का फिजिकल मीनिंग रहता है दैट इज बेसिकली एरिया अंडर द ग्राफ, एरिया अंडर द कर्व। You got it or not? तो अब आपको सिर्फ और सिर्फ इस कॉन्सेप्ट को, इसमें कुछ भी ऐसा मैथमेटिकल कैलकुलेशन इन्वॉल्व नहीं है, दिस इज सिंपली बेस्ड ऑन दिस कॉन्सेप्ट कि आपको एक्सपेंशन हो रहा है, आपको वर्क डन निकालना है, और ये एक कॉन्सेप्चुअल बेसिक अंडरस्टैंडिंग के ऊपर क्वेश्चन फ्रेम किया गया है। वन ऑफ द इंपॉर्टेंट क्वेश्चन, क्या वर्क डन हमारा कॉन्टिन्यूसली इंक्रीज हो रहा है, क्या वर्क डन हमारा कॉन्टिन्यूसली डिक्रीज हो रहा है, क्या वर्क डन हमारा पहले इंक्रीज फिर डिक्रीज हो रहा है, और या फर्स्ट डिक्रीजेस देन इंक्रीजेस, व्हाट इज द बेस्ट ऑप्शन। तो जैसा आप देख पा रही हैं, अगर हम लेट सपोज इस कर्व में सिर्फ इतने पार्ट को भी ऑब्जर्व करते हैं, तो आप देख पा रहे हैं जैसा आपने बोला कि वर्क डन के लिए मुझे P डेल्टा V को इंटीग्रेट करना है, और इसमें मेरा सिस्टम काम कर रहा है वर्क डन बाय द सिस्टम, मतलब मैं एक्सपेंशन की बात कर रहा हूं। तो आप देख सकते हैं जैसे ही आप इस पॉइंट से इस पॉइंट पर आते हैं, आपका वॉल्यूम बढ़ रहा है। सो आई थिंक दिस मच इज क्लियर। तो डेफिनेटली हम लोग वर्क डन बाय द सिस्टम की बात कर रहे हैं। तो अभी आपने बताया इस वर्क डन को निकालने के लिए आपको ये एरिया फाइंड आउट करना है, सिंपल, गॉट इट। तो आप देख सकते हैं आपके पास ये एरिया। अब आप इस पॉइंट से नेक्स्ट पॉइंट पर चलते हैं, यहां पर आप फिर वॉल्यूम एक्सपैंड कर रहा है, वॉल्यूम बढ़ रहा है। यहां पर इस पर्टिकुलर रीजन के लिए ये एरिया निकाल लीजिए। अगले कॉन्सेप्ट में अब आप देखिए, काफ़ी बच्चा इसको क्या अज्यूम कर रहा है, वो इसी एरिया की बात कर रहा है। वो कहता है सर ये एरिया ज़्यादा था, ये एरिया कम था। इसका मतलब पहले आपका एरिया कम होता जा रहा है क्योंकि आप सिर्फ इतने पार्ट को ऑब्जर्व कर रहे हैं। फिर आप कहते हैं नहीं सर, अब आपका यहाँ के कंपैरेटिवली इस रीजन में एरिया बढ़ गया, सर और बढ़ गया। इसका मतलब एक बच्चा सिर्फ इतने स्ट्रिप्स के एरिया को ही इंटरप्रेट करता है और वो आंसर देता है कि पहले डिक्रीज हो रहा है देन इंक्रीज हो रहा है, और वो इस फोर्थ ऑप्शन को टिक करता है, विच इज अ रॉन्ग ऑप्शन। व्हाई इट इज रॉन्ग, ट्राई टू अंडरस्टैंड। हमें इस इनिशियल पोजीशन से इस फाइनल पोजीशन तक पूरे कॉन्सेप्ट को इन टोटलिटी ऑब्जर्व करना है। और अब आप इसको पॉइंट 1 से पॉइंट 2 तक ऑब्जर्व करेंगे, तो जैसे जैसे आप आगे फ्लो कर रहे हैं, आप इस एरिया में ये एरिया ऐड कर दीजिए, थर्ड एरिया ऐड कर दीजिए, फिर आप फोर्थ एरिया ऐड कर दीजिए। इसका मतलब इन टोटलिटी आपका एरिया जो है पूरे प्रोसेस में बढ़ता जा रहा है। इसका मतलब अगर मेरा टोटल एरिया बढ़ता जा रहा है, तो जो मेरा वर्क डन है वो कॉन्टिन्यूसली क्या हो रहा है, इंक्रीज हो रहा है। सो दिस इज द ओनली ऑप्शन जो यहां पर करेक्ट है। आई होप हम सब लोग इस कॉन्सेप्ट को बिल्कुल क्लैरिटी के साथ समझ चुके हैं। इफ यू हैव स्टिल एनी डाउट, प्लीज रेज योर हैंड और प्लीज कंफर्म इट। सो रविंदर हैज given me the first option. Yes Ravinder, good, keep it up. और कुछ जानना चाहते हैं या किसी को कोई डाउट है तो पूछ सकते हैं बच्चों। Shall we? तो क्या हम एक कॉन्सेप्ट और यहां पर समझ सकते हैं? चलिए नाउ अब यहां पर एक सिचुएशन बिल्डअप करते हैं। सो कंसिडर a PV कर्व, गॉट इट। और यहां पर हम लोग वॉल्यूम 1, वॉल्यूम 2, प्रेशर 1, प्रेशर 2, लेट्स लेबल इट एज A, B, C। और आप अपने थर्मोडायनेमिक प्रोसेस को A से B, B से C और C से A पर मूव करवाते हैं। गॉट इट और नॉट? अभी हम यहाँ पर यूनिट्स की बात नहीं कर रहे, बट अगर आप चाहें तो यहाँ पर आप यूनिट्स को मेंशन कर सकते हैं। प्रेशर इज इन एटमॉस्फेरिक प्रेशर और ये हमारे पास सीसी में है। सीसी स्टैंड फॉर क्यूबिक सेंटीमीटर। तो हर छोटे से छोटे इस कॉन्सेप्ट को आपको समझना है कि अगर इस टाइप का न्यूमेरिकल आता है तो अब आपको कैसे अप्रोच करना है। गॉट इट? नाउ अब आपसे पूछा जाता है कि अगर हम वर्क डन ए से बी पर आते हुए, सो इफ आई आस्क यू व्हाट इज द वर्क डन बाय दिस गैस और दिस सिस्टम अलोंग ए टू बी पाथ, तो ध्यान दीजिए वर्क डन का बेसिक कॉन्सेप्ट था P इंटू डेल्टा वी। जब आप A से B पर आ रहे हैं, क्या आपके पास वॉल्यूम में कुछ चेंज हो रहा है? वॉल्यूम में चेंज नहीं हो रहा, तो इस A से B के रास्ते पर आपके पास वर्क डन क्या रहेगा बच्चों? 0। नाउ अब अगर हम वर्क डन B से C पर इस प्रोसेस में बात करते हैं, वर्क डन फ्रॉम B टू C, गोइंग बाय द सेम फॉर्मूला, यहाँ पर जो प्रेशर है वो P1 है, वॉल्यूम V2 माइनस V1 है। ध्यान से ऑब्जर्व कीजिए, जब आप B से C पर पहुंच रहे हैं, क्या आपका वॉल्यूम बढ़ रहा है? इज इट इंक्रीजिंग? यस, वॉल्यूम बढ़ रहा है। इसका मतलब हम एक्सपेंशन स्ट्रोक की बात कर रहे हैं, तो ये वर्क डन साइन कन्वेंशन में क्या रहेगा बच्चों? पॉजिटिव। यू गॉट इट और नॉट? अब यहां पे P V2 माइनस V1, ध्यान देने वाली बात है कि इस P और V का जो प्रोडक्ट जब आप डिफाइन करेंगे तो दोनों यूनिट्स को स्टैंडर्डाइज करना बिल्कुल मैंडेटरी है। नो चॉइस, नो थॉट अबाउट इट। जब आप P डेल्टा V करेंगे तो P भी स्टैंडर्ड SI यूनिट में होनी चाहिए और वॉल्यूम भी हमारे पास स्टैंडर्ड SI यूनिट में होना चाहिए। तो देन ओनली यू कैन डिफाइन दिस प्रोडक्ट इन स्टैंडर्ड SI यूनिट्स, और तब हम इस वर्क डन के यूनिट्स को जूल असाइन कर सकते हैं। गॉट इट और नॉट? सो दिस इज कॉन्सेप्ट। अभी हम एक न्यूमेरिकल पिक कर लेंगे यहां पर। नाउ व्हेन यू मूव फ्रॉम C टू A, अब जब आप C से A मूव करते हैं, B से C मूव किया, तो दिस वाज द एरिया जो आपने P डेल्टा V से डिफाइन किया। दिस वाज P, दिस वाज डेल्टा V, और हमने इस एरिया को डिफाइन किया। अब C से A, अब देखिए C पर वॉल्यूम V2 था और A पर आपका वॉल्यूम V1 है। अगर आप ध्यान से देख पा रहे हैं तो शायद आपका वॉल्यूम कम हो रहा है, तो इट मीन्स दिस इज वर्क डन बाय द सिस्टम और ऑन द सिस्टम, compression on the system. So this is work done on the system, और डेफिनेटली ये क्या रहेगा? नेगेटिव। क्या रहने वाला है ये? नेगेटिव, दैट इज फॉर श्योर। और दिस वाज जो फर्स्ट सिचुएशन था, इसमें ये था वर्क डन बाय द सिस्टम। सो दिस इज ऑल्सो क्लियर। अब वर्क डन के लिए आपको एरिया फाइंड आउट करना है, तो एरिया मीन्स ये वाला सारा एरिया आपको डिफाइन करना है, एंड दिस इज टिपिकली द शेप ऑफ अ ट्रेपीजियम। सो दैट मीन्स यू हैव टू फाइंड आउट एरिया ऑफ ट्रेपीजियम। नेगेटिव साइन रहेगा, आप लिख सकते हैं ट्रेपीजियम का एरिया क्या रहता है बच्चों? हाफ इंटू सम ऑफ पैरेलल साइड्स। तो क्या आप देख पा रहे हैं, एक साइड P2 है, एक साइड P1 है, सो सम ऑफ पैरेलल साइड्स into height. Can you see the height of this? And this is also V2 minus V1. अब V2 आपका बड़ा है, V1 छोटा है, तो आप लोगों के पास नेगेटिव साइन कैसे बना? I think you people got it because this is negative volume. Got it? So V1 and V2. So this is all about this process. अब अगर यहाँ पर एक छोटा सा न्यूमेरिकल वैल्यू असाइन करते हैं, लेट सपोज हम लोग V1 को, लेट मी मेक यूज ऑफ सम इंटरेस्टिंग कलर जिससे थोड़ा सा आप लोगों के लिए, लेट्स पिक द ब्लू। तो यहाँ पर हम लोग P1 को 1 एटमॉस्फेरिक टू कीप इट सिंपल एंड P2 को हम लोग 2 एटमॉस्फेरिक पुट करते हैं। V1 को लेट्स पुट इट एज 2 cc एंड V2 को लेट्स कीप इट एज 4 cc। गॉट इट? नाउ interesting area to observe. If I ask you work done from A to B to C to A, very interesting. आप A से शुरू हुए एक पाथ फॉलो करते हुए you are coming back to A. It means this is basically a cyclic process. Got it? साइक्लिक प्रोसेस में अभी आप लोगों ने एक फीचर सीखा, देयर वुड बी नो चेंज ऑफ इंटरनल एनर्जी। इंटरनल एनर्जी में कोई चेंज नहीं आएगा। दैट इज ऑल्सो वेरी इंपॉर्टेंट कॉन्सेप्ट। बट अगर आप यहाँ पर वर्क डन की बात कर रहे हैं तो वर्क डन आपको ये तीनों स्टेजेस का ऐड करना पड़ेगा एंड व्हाट इज द नेट वर्क डन? नेट वर्क डन वुड बी गिवन बाय दिस रीजन। ये कॉमन पार्ट कैंसिल हो जाएगा दोनों में एंड दिस इज नेट वर्क डन वुड बी एरिया ऑफ दिस ट्रायंगल ABC एंड दिस इज इन एंटी क्लॉकवाइज फैशन। तो इस वर्क डन का जो न्यूमेरिकल वैल्यू रहेगा दैट वुड बी इन नेगेटिव। यहां तक समझने में किसी को कोई डाउट? नुमेश, ऋतु, राज, संजना, एनी डाउट? फाइन। सो जब हम इस नेट वर्क डन की बात करेंगे तो हम लोग इस एरिया ऑफ ट्रायंगल की बात कर रहे हैं बच्चों। तो नाउ लेट्स कम बैक टू द सेम न्यूमेरिकल प्रॉब्लम। सो द ट्रायंगल का एरिया क्या रहता है? हाफ इनटू बेस इनटू हाइट। So that means half, negative sign would be there, V2 minus V1, so that gives you delta V as 2 cc and P2 minus P1, 2 minus 1 atmospheric pressure. अगर मुझे इस न्यूमेरिकल वैल्यू को, नेगेटिव साइन क्यों आ रहा है हम लोग क्लियर कर चुके हैं, तो नो नीड टू, लेट्स बी मोर फोकस्ड फॉर द न्यूमेरिकल कैलकुलेशन। नाउ हाफ इंटू 2 cc क्यूबिक सेंटीमीटर, हमें इसको यूनिट को कन्वर्ट करना है SI सिस्टम में। सो दैट मीन्स 1 सेंटीमीटर इज 10⁻², सो दैट वुड बी 10⁻³ cubic meter. So this is the first thing you need to be careful. And 1 atmospheric 1.01, or you can simply take it as 1 for the numerical calculation, 10⁵ Newton per meter square, and when you multiply this, this would give you the answer in joules. So this is the interesting story behind this, the whole concept of developing this numerical, कि आप लोगों के पास जो यहाँ पर सबसे बड़ा एक जो यहाँ पर फ्लॉ रहता है कि बच्चा इसको यूनिट में कन्वर्जन नहीं करता प्रॉपरली, और वहाँ से आंसर यूजुअली गलत हो जाता है. तो वी हैव टू बी वेरी पर्टिकुलर अबाउट दिस कन्वर्जन पार्ट वाइल डूइंग द न्यूमेरिकल्स. एनी डाउट फ्रॉम दिस पार्ट? यहाँ से किसी को समझने में कोई चैलेंज, कोई डाउट है तो प्लीज़ रेज योर क्वेश्चन. सो राज, आई होप यू पीपल हैव अंडरस्टूड इट. आप समझ गए नेगेटिव साइन क्यों आया है. जब आप इस बड़े एरिया में से छोटा एरिया माइनस करेंगे तो दैट वुड गिव यू नेगेटिव, क्योंकि ये कॉम्प्रेशन नेगेटिव में है. इस नेगेटिव में से ये वाला पॉजिटिव एरिया माइनस करेंगे तो अल्टीमेटली आपके पास नेगेटिव क्वांटिटी ज़्यादा बड़ा एरिया था, इसलिए वो नेट रिजल्टेंट नेगेटिव वैल्यू रहेगी. एनी डाउट? सो क्या हम आगे चल सकते हैं? सो लेट्स मूव. नाउ वी हैव फर्स्ट लॉ ऑफ thermodynamics. This is the beginning of your chapter in a more interesting way now. Now first law, जैसा अभी हमने एक पीछे concept discuss किया, this law was established much before the zeroth law, और rather second law भी develop हो चुका था. अब उसके बाद जब zeroth law या उस thermal equilibrium के concept को एक law का statement दिया गया, fundamental, that was more fundamental to your thermodynamics, तो वहाँ पर keeping the importance of temperature intact, उस law को इस first law से पहले place किया गया, and scientists लोग they didn't have any option, they had to place it before the first law, and they had to call it as the zeroth law. So what do you mean by first law? First law is basically in accordance with law of conservation of energy. This is the beauty of this law. This is the best part कि जो first law है वो एक energy conservation law का ही एक form है, and according to Clausius statement, first law of thermodynamics states if heat is given to the system, heat is basically a form of energy, and that is always in transition. Heat is also not a state function. It's again a path dependent. You got it or not? Heat can be added, heat can be removed from the system. So this heat energy may or may not change the internal energy. So heat. Now this time we are talking about heat is given to the system. So if heat is given to the system, then the system will absorb this heat. So some part of this heat will be utilized in raising the internal energy of the system, and with the rest the system can perform some work. So that means this is the first law that is purely in accordance with energy conservation law. So if heat is added, some part of it may be utilized in increasing the internal energy. That depends on how you are adding the heat, and the rest may be in increasing or by doing some work done. Got it or not? Now sign convention says if heat is supplied to the system, if heat is added to the system, it is taken as positive. If heat is removed from the system, if it is taken from the system, then it would be taken as negative. If there is increase in internal energy, that would be taken as positive. If there is decrease in internal energy, that would be taken as negative. Got it? Work done by the system, positive, on the system, negative. So these are the sign conventions which you people will be clearly utilizing or using all these sign conventions while attempting this, and this law can be applied to any of the thermodynamic processes you have. Then based on this, let's attempt a numerical. For a gaseous system, find change in internal energy if heat is supplied to the system is 50 joules and work done by the system is 16 joules. So what it says, first law says delta Q is equal to delta U plus some work done. So this is there. If heat is supplied to the system, that means this is 50 joules. Supplied means positive. Got it? Work is done by the system, that is taken as positive. This is 16 joules. And we have to find out change in internal energy. So that means 50 minus 16. That gives you 34 joules as your change in internal energy. So this is the simplest of all the numericals, and this is just to make you understand how you people have to apply your sign conventions while attempting numericals based on the first law of thermodynamics. Any doubt? Raj has given me the right answer. Very good, Raj. Shall we move? Now, specific heat capacity. So when you talk about specific heat capacity, so let's understand heat. So heat given to a system of mass m, its specific heat is this, and change in temperature is delta T. So Q is equal to mc delta T. For a gaseous system, so this C, specific heat at constant pressure. So specific heat at constant pressure for 1 mole of the gas, that is Cp. So this is for molar specific heat. And similarly, we have molar specific heat at constant volume is Cv. This is again, I'm talking about molar specific heat. And we know Cp is always greater than Cv, and Cp minus Cv is equal to R, where R is your universal gas constant. Got it or not? Also, very interesting. So Cp minus Cv is equal to R. Cp by Cv is, this ratio is defined as gamma also. So just find out the value of Cp. So that is gamma times Cv. So put the value of Cp over here. So gamma Cv minus Cv is equal to R. So it gives you value of Cv as R upon gamma minus 1, and Cp is gamma times Cv. So this is gamma R upon gamma minus 1. So you have all these fundamental formulas which are there. Any doubt from this part? Anything you would like to ask? कुछ भी पूछना चाहेंगे? Cp, Cv. Now, let's suppose you apply this for monatomic gas. Can you give me the value of gamma for monatomic gas? Anyone? Gamma for monatomic gas. Yes? It's 5/3. So put the value of gamma over here, and that gives you Cv as what? So R upon 5/3 minus 1, and that gives me 5 minus 3, 2, and this becomes 3/2 R. And when you put the value in this, so that gives you Cp as 5/2 R. So this is for monatomic, and similarly for diatomic gas, what is the value of gamma? 7/5. So that gives me the value. When you put 7/5 over here, so that gives me 5/2 R and Cp as got it. Similarly, we can do it for triatomic gas also. So this is the importance of keeping all the formulas intact. अगर आपको ये छोटे छोटे formulas याद हैं बच्चों, तो you can play with all these formulas for your numerical purposes. Any doubt from this part? इसमें से किसी को कुछ समझने में challenge है? Raj has given me the right answers. Very good, Raj. So let's move to thermodynamic state variables and equation of state. So thermodynamic state variables. So thermodynamic state variables are that defines the thermodynamic state of your gaseous system. So thermodynamic state variables that defines the thermodynamic state of any system, and primarily we have P, V, T. So these are the three variables that define the thermodynamic state of any system, and usually they all are defining the ideal gas equation as PV is equal to nRT, where P is the pressure, V is the volume, N, small n stands for number of moles, R stands for universal gas constant, and T is the absolute temperature, that is in Kelvin. So this is ideal gas equation. So ideal gas equation, PV is equal to, here they are writing number of moles as mu. One and the same thing. You keep it as mu or you keep it as n, this is your personal choice. But हमारे लिए ideal gas equation PV is equal to nRT या mu RT, जो भी आप समझना चाहें. Got it? Any doubt from this part? Now we have thermodynamic state variables are of two kinds. Intensive variable. क्या रहता है intensive variable? Variables which are independent of the size, independent of the number of molecules. I mean like independent. हमें फ़र्क नहीं पड़ता there are 5 molecules or there may be 50 or there may be 500 molecules. So the best example is pressure, density, temperature. So these all are intensive variables which are independent of the size of the system. Then we have extensive. Definitely that depends on the size of the system. That is important. So very first thing coming to your mind, extensive, size, volume. So if you are keeping 5, so they'll occupy this much. If you are keeping 50 molecules, they'll definitely occupy a bigger size. 500 will definitely have a much bigger size comparatively. So it means volume is defined by the number. Then mass, when you keep on adding more molecules to your system, more molecules gaseous system, so definitely the mass of the whole gaseous system would keep on increasing. So that means mass is also an extensive variable. Any doubt? Any doubt? Shall we move? Then thermodynamic processes. We have varieties of ways by which a thermodynamic system can interact with the surrounding. So very first, quasi-static process. Quasi, pseudo, false. Static seems to be at rest, जिसमें कोई हरकत नहीं हो रही. It means system is almost in equilibrium with surrounding, though changes are happening, but these changes are at very, very, very small rate, such that the system would remain in equilibrium. What kind of equilibrium? That would be a thermal equilibrium, that would be a mechanical equilibrium. So the system would remain in equilibrium with the surrounding, but this is just a pseudo concept because system is changing at a very, very slow pace. So an idealized process, not possible exactly in real life situations, so idealized process in which at every stage, whenever you observe the system with respect to surrounding, system is in equilibrium state. And such a process which happens at very, very slow rate, infinitely slow, this is quasi-static, means nearly static process, which is not the true case, nearly. Pseudo word. The system changes its variables. Whenever system interacts, whenever system changes, so system is defined by variables. These variables are primarily your pressure, volume and temperature. So the variables may change, but they change so slowly that it remains in thermal equilibrium, it remains in mechanical equilibrium with its surrounding. So this is quasi-static process. Isothermal, the next process is isothermal process. Isothermal process. एक ऐसा process, this is adjective ending, iso means same, therm means temperature. So condition pertaining to same temperature. It means हमारे पास process change हो रहा है, लेकिन temperature system में change नहीं हो रहा. प्रेशर चेंज हो सकता है, वॉल्यूम चेंज हो सकता है फॉर अ गिवन अमाउंट, फॉर अ गिवन गैस, लेकिन टेम्परेचर चेंज नहीं होगा. सो टेम्परेचर रिमेन्स कांस्टेंट. डेल्टा टी इज 0 when there is no change in temperature, there is no change in internal energy. Got it? So internal energy change would also be 0. Now, if you look at the ideal gas equation, PV is equal to nRT for a given amount, it means number of moles are already defined or taken as constant. R is gas constant, T is also kept constant, so this part is constant. So shall I say PV remains constant? Got it? So pressure volume product will remain constant, no change in temperature. And usually these processes happen at a slow rate. You got it or not? Because it will not allow the temperature to be changed. Now apply your first law. First law says delta Q is equal to delta U plus P delta V. So if you look at this, for isothermal process, change in internal energy is 0, so this part would not be there. So whatever heat is there, that is basically P delta V. So if heat is added, please note it down, if heat is added taken as positive, P delta V would also be positive, and this shows there would be an expansion stroke, and this is work done by the system. So what it means? It means whatever heat you are adding at constant temperature for the isothermal processes, the whole of the heat will be utilized in expanding the gas, so that would be consumed in basically work done by the system. And if heat is taken, so that would also be negative, and this is compression stroke, and this is work done on the system. So this is work done on the system. You got it or not? So I hope you are clear on these two aspects. So isothermal process एक ऐसा प्रोसेस जिसमें टेम्परेचर चेंज नहीं होता, प्रेशर और वॉल्यूम का प्रोडक्ट कांस्टेंट है. प्रेशर चेंज हो सकता है, इसका मतलब प्रेशर इज इनवर्सली प्रोपोर्शनल टू वॉल्यूम. गॉट इट? इसका मतलब जैसे जैसे आपका प्रेशर या वॉल्यूम बढ़ेगा, प्रेशर आपका कम होगा, एंड दिस इज अ रेक्टेंगुलर हाइपरबोला इनवर्स फंक्शन। प्रेशर वॉल्यूम को अगर मैं प्रेशर के विद रिस्पेक्ट प्लॉट करता हूं तो प्रेशर वॉल्यूम का प्रोडक्ट कांस्टेंट है। अगर प्रेशर वॉल्यूम को मैं वॉल्यूम के विद रिस्पेक्ट प्लॉट करता हूं तो ये प्रोडक्ट भी कांस्टेंट है। प्रेशर को अगर मैं 1 बाय वॉल्यूम के विद रिस्पेक्ट प्लॉट करता हूं तो ये ग्राफ वुड बी ए स्ट्रेट लाइन पासिंग थ्रू दिस ओरिजिन। एनी डाउट फ्रॉम दिस पार्ट? यहां तक समझने में किसी को कोई चैलेंज? राज, संजना, एनी डाउट? मनोज? चलिए, now work done in an isothermal process. This is quite interesting. Though formula is there, would you like me to derive this relation? Okay, so let's suppose we have PV is equal to nRT for isothermal process, and you are keeping this nRT as constant C. Got it? So this is a constant. Got it? Now for isothermal process, so let's suppose the small work done, we have just understood it as P delta V. हमारा गैस एक्सपैंड करता है और हमारा गैस एक्सपैंड कर रहा है, वॉल्यूम चेंज हो रहा है, तो हमारा वॉल्यूम V1 से V2 है। यू गॉट इट? सो टोटल वर्क डन के लिए हम इसको एक्सप्रेशन को इंटीग्रेट करने वाले हैं। प्रेशर को क्या हम यहाँ से nRT बाय V पुट कर सकते हैं? सो देन दिस इंटीग्रल बिकम्स dV बाय V फ्रॉम V1 टू V2। nRT कांस्टेंट है, dV बाय V इसका इंटीग्रेशन नेचुरल लॉग V फ्रॉम V1 टू V2, and this is nRT ln V2 by V1। इस नेचुरल लॉग को जब हम लॉग बेस 10 में कन्वर्ट करते हैं तो वी कीप इट एज 2.303 nRT log base 10, that would be V2 by V1। So this becomes the expression for the work done। यहाँ पर अभी भी नंबर ऑफ मोल्स के लिए म्यू वर्ड यूज़ किया है, इट हार्डली मैटर्स। सो दिस इज़ द वन, और यहाँ से अगर आप इसको P1 V1 इज इक्वल टू P2 V2 यूज़ करते हैं तो व्हाट डू मीन बाय V2 बाय V1? सो हम इस एक्सप्रेशन को अगर कीपिंग म्यू एज नंबर ऑफ मोल्स लॉग बेस 10 P1 by P2, so this is another form for the work done by or work done during your isothermal process. Any doubt? यहाँ से बच्चों कुछ पूछना चाहेंगे? Anything you would like to confirm or ask? So there is no big no. Shall we move? नाउ ग्राफ फॉर आइसोथर्मल प्रोसेस। ये ग्राफ अभी हम लोगों ने डिस्कस किया, कीपिंग PV एज कांस्टेंट, सो प्रेशर इज इनवर्सली प्रोपोर्शनल टू वॉल्यूम, दिस पार्ट वी हैव ऑलरेडी डिस्कस्ड। और अगर बच्चों यहाँ से अगर आपको पूछा जाता है, इफ़ आई आस्क यू टू फाइंड आउट द वर्क डन ड्यूरिंग दिस, तो कैन यू फाइंड आउट द एरिया अंडर द कर्व, एंड दैट गिव्स मी द वर्क डन ड्यूरिंग दिस एक्सपेंशन स्ट्रोक। सो दिस ग्राफ इज बेसिकली फॉर द एक्सपेंशन, और यहाँ पे वर्क डन पॉजिटिव रहने वाला है, दैट इज बाय द सिस्टम। आई एम रीइटरेटिंग अगेन एंड अगेन द सेम कॉन्सेप्ट कि जब भी वर्क डन हमारा एक्सपेंशन स्ट्रोक की बात हो रही है तो वर्क डन पॉजिटिव रहता है, एंड दिस इज वर्क डन बाय द सिस्टम। गॉट इट? सो यहाँ पर आप देख सकते हैं एक्सपेंशन स्ट्रोक की ही बात करी है। एक्सपेंशन स्ट्रोक में आपका वॉल्यूम बढ़ रहा है लेकिन टेम्परेचर हैज़ टू बी constant, so this is the graph। then P versus T ग्राफ आप देख सकते हैं, जैसे जैसे वॉल्यूम बढ़ रहा है प्रेशर कम हो रहा है, लेकिन टेम्परेचर रिमेन्स कांस्टेंट। सो ये सारे के सारे जितने भी ग्राफ्स हैं, ये सब कीपिंग दिस प्राइम ग्राफ एज एक्सपेंशन स्ट्रोक इन माइंड, इनको देखकर बनाए गए हैं। और अगर आप यहाँ से कॉम्प्रेशन स्ट्रोक की बात करें तो कॉरस्पॉन्डिंग पीवी ग्राफ, अगर मैं पर्टिकुलरली कॉम्प्रेशन की बात करूं तो कैन यू लुक एट दिस ग्राफ एज योर कॉम्प्रेशन स्ट्रोक पीवी ग्राफ। हम देख सकते हैं यहाँ पर हमारे पास पीवी में वॉल्यूम कम हो रहा है और कॉरस्पॉन्डिंगली प्रेशर बढ़ रहा है। डू वी अंडरस्टैंड? सो अब देखिए, इस कॉम्प्रेशन स्ट्रोक में हमारे पास वॉल्यूम कम हो रहा है, प्रेशर बढ़ रहा है। तो अगर कॉरस्पॉन्डिंग V वर्सेस T ग्राफ बनाना हो, वॉल्यूम कम हो रहा है, टेम्परेचर कांस्टेंट रहेगा, वॉल्यूम कम हो रहा है, टेम्परेचर कांस्टेंट रहेगा। कैन यू सी दिस कॉरस्पॉन्डिंग ग्राफ? और ऐसा ही ग्राफ अगर P और T के लिए बनाना पड़े तो आप देख सकते हैं यहाँ पे प्रेशर बढ़ रहा है, टेम्परेचर अभी भी कांस्टेंट है। तो लुक एट द corresponding graphs for your compression stroke also. I hope expansion और compression के ग्राफ्स को आप समझ पाए हैं। Shall we move? चलिए, the next process हम लोग यहाँ पर इंट्रोड्यूस करना चाहेंगे adiabatic process. Adiabatic. So what do you mean by adiabatic process? So adiabatic process क्या है बच्चों? So let's suppose you have a system. So this is your system and this is your surrounding part. No heat transfer takes place. System और surrounding को permission नहीं है कि इनके बीच में कोई भी heat exchange हो सके, तो definitely डेल्टा Q क्या रहने वाला है बच्चों? 0। ये तभी पॉसिबल है जब सिस्टम के बाहर जो वॉल है दैट इज इंसुलेटिंग वॉल, थिक इनफ दैट डज नॉट अलाउ द हीट टू गेट एस्केप्ड और हीट टू एंटर द सिस्टम। सो यहाँ पर हमारे लिए डेल्टा Q 0 रहने वाला है। यू गॉट इट और नॉट? अब लेट्स सपोज इफ यू अप्लाई योर फर्स्ट लॉ सेज change in internal energy plus P delta V. So this is delta Q is equal to delta U plus P delta V. So it means delta U is equal to minus P delta V. This is interesting. अब अगर आप ध्यान दे रहे हैं, let's suppose P delta V पॉजिटिव है। P delta V पॉजिटिव कब रहने वाला है? एक्सपेंशन स्ट्रोक में। एक्सपेंशन स्ट्रोक का मतलब क्या है? वर्क डन बाय द सिस्टम। इसका मतलब अगर मेरी गैस एडियाबेटिकली एक्सपैंड करती है, एक्सपैंड, वर्क डन पॉजिटिव रहता है, डेल्टा यू क्या है यहाँ पर? नेगेटिव। गॉट इट और नॉट? इसका मतलब मेरी इंटरनल एनर्जी फॉल करेगी, मेरा टेम्परेचर फॉल करेगा। So very important. So if a gas is allowed to expand adiabatically, टेम्परेचर इसका फॉल कर रहा है, so gas cools off. मतलब गैस का टेम्परेचर कम होने वाला है, गैस ठंडी होने वाली है। सेम वे में इफ़ यू से डेल्टा यू, अब कीपिंग दिस नेगेटिव इंटैक्ट, हम पी डेल्टा वी को भी नेगेटिव लेते हैं। पी डेल्टा वी नेगेटिव कब रहता है? कॉम्प्रेशन स्ट्रोक में। सो दिस इज वर्क डन ऑन द सिस्टम। अब वर्क डन ऑन द सिस्टम में डेल्टा यू क्या आ रहा है बच्चों? This negative gives you what? Positive. इसका मतलब मेरा temperature बढ़ने वाला है. So it means if gas is allowed to compress adiabatically, it gets heated up. हमारी गैस का टेम्परेचर बढ़ने वाला है. डू वी अंडरस्टैंड दिस? सो दिस इज समथिंग इंटरेस्टिंग. एक और प्रोसेस है बच्चों, या इस प्रोसेस की एक और खासियत है. इट हैपन्स एट अ वेरी फास्ट रेट. इसका एडियाबैटिक प्रोसेस का जो होने का जो रेट है वो इतना फास्ट है कि दैट वोंट अलाउ यू, आपको वो मार्जिन ही नहीं दे रहा हीट एक्सचेंज करने के लिए. लाइक अ सडन बर्स्ट ऑफ अ टायर. अगर हमारा टायर एकदम फट जाता है, बर्स्ट हो जाता है, गैस एस्केप्स, डज नॉट गिव यू चांस टू एक्सचेंज हीट. सो देयर वुड बी नो exchange of heat. और अदरवाइज सिस्टम इज वेल इंसुलेटेड. इतनी थिक वॉल्स हैं कि बाहर की हीट अंदर एंटर नहीं कर सकती, अंदर की हीट बाहर नहीं जा सकती, एंड दैट डोंट अलाउ यू. सो गॉट इट और नॉट? एंड एडियाबैटिक प्रोसेस का जो इक्वेशन है दैट इज PV raised to power gamma is constant. So this is important. PV raised to power gamma. गामा हम ऑलरेडी इंट्रोड्यूस कर चुके हैं एज रेशियो ऑफ CP by CV. दिस वी हैव ऑलरेडी इंट्रोड्यूस्ड. एनी डाउट फ्रॉम दिस पार्ट? यहाँ से आप कुछ पूछना चाहेंगे? Shall we move? Work done in an adiabatic process. This is quite interesting. So let's begin the process. PV raised to power gamma is constant. Got it? So let's suppose from initial condition, initial state P1 V1, because this is a thermodynamic process, so PV raised to power gamma, it moves to a new thermodynamic state P2 V2 gamma. So this is actually the adiabatic process. Now likewise we did it earlier also. The small work done is P delta V. So we are taking the gas from V1 to V2. So let's use this process. So shall we put P as C by V power gamma. So this is V minus gamma dV from V1 to V2, and that defines the work done during the or work done in an adiabatic process. So what it becomes? V power minus gamma plus 1 minus gamma plus 1 into C. Do we? Now take this C inside this. So when the moment you take C inside the bracket, let's put C as this one also. Or first let me just introduce C inside the bracket and let me put the limits out there. So first this is V2 minus gamma plus 1 minus V1 minus gamma plus 1. You got it? And this is minus gamma plus 1. So moving to the next step. Now when you change the sign of this, so these two has to be replaced. So V1 minus gamma plus 1 can also be written like this, minus V2 V2 is what? V2 minus gamma V2. And you know, when you multiply this C with both the terms, so this C would definitely be there, and because we have replaced the signs over there, so minus gamma plus 1 means it becomes gamma minus 1. Now let's put the value of C. In the first part, let it be P1 V1 power gamma. Then you have this one, V1 power minus gamma V1 minus, for this C, let's put P2 V2 power gamma. So this is P2 V2 power gamma, V2 power minus gamma into V2, the whole divided by gamma minus 1. So this is how you'll be solving this, and this is very important as far as your school part is concerned. So this goes, so P1 V1 minus P2 V2 by gamma minus 1 would ultimately be the work done, expression for work done. And this P1 V1 can also be written as, if I keep it as N R T1 minus T2 by gamma minus 1. So this is the expression for work done in an adiabatic process. Any doubt from this part? Anything you would like to ask, anything you would like to confirm? So let's move. Now graph for adiabatic process. So we have just understood PV raised to power gamma as constant. So for that we have this graph. Now using your equation PV is equal to nRT, got it or not? Let's put the value of P as nRT by V. When you put the value in this one, so nRT by V, and this is V power gamma, that remains constant, got it? So nR, this is constant, so when you take it below the constant will remain constant, so this is T power 1 and this is V power gamma minus 1, that remains constant. So we have this equation, and this is the graph for TV raised to power gamma minus 1 as constant. Similarly, we can have this equation also. Instead of substituting P, let's suppose you substitute the value of V, you will end up with this equation, and this is the next equation for your adiabatic process in terms of P and T. So these are the graphs for the adiabatic processes we have. Then let's have a numerical. A mass of dry air at NTP is compressed to 1 by 32 of its original volume suddenly. If gamma is equal to 1.4, the final pressure would be, okay? So using P1 V1 gamma is equal to P2 V2 gamma. So P1 at NTP, so this is 1 atmospheric pressure, so this is P, got it? We have to find out P2. So initial volume is V, and when you take V2 over here, so that is 1 by 32 times V, and we'll keep gamma over here, and that gives me the expression for this P2. So this goes with this 32, shall I put it as 2 power 5, got it? And what is the value of gamma? Gamma as 7 by 5, so that gives me P2. So this 5 goes with this, and 2 power 7 gives me 128. This pressure is NTP, that means standard atmospheric pressure, so this is P2. So P2 comes out to be 128 atmospheric pressure. So I hope everyone is clear on this point also. Isochoric process, the name suggests there is no change in volume, So delta V is 0. It means work done would definitely be 0. Whatever heat you add to the system, that will primarily be used in increasing or decreasing the or change in the energy. This process that involves volume of a thermodynamic system as constant, this is called isochoric process. The other name, don't get confused, this is isometric process also. And because there is no change in volume, so PV graph is definitely there. No change in volume, so VT graph is there. Now P versus T graph. So using PV is equal to nRT. So P by T is nR by V. So volume is constant, nR is constant, so the whole term is constant. P by T, that is slope of P versus T curve, remains constant, and that is why you have a straight line curve. Got it? Isobaric. The next process, isobaric, bar stands for pressure. So that means pressure remains constant. So there is no change in pressure. So when you talk about work done, this work done is P delta V. So volume changes. Usually whatever processes we are discussing, we are keeping the pressure constant. Usually we are doing it at constant atmospheric pressure, so keeping the pressure constant. So work done by the gas would definitely be there. So P V2 minus V1, or in terms of temperature as mu R T2 minus T1. Pressure remains constant. Volume can increase or decrease depending on the expansion or the compression. Same way, using PV is equal to nRT. This is V by T curve. So nR by P. This part is constant. This is again the slope that goes constant. So we have a straight line. For PT curve, pressure remains constant. Temperature can increase or decrease depending, because when you apply your this law, this is there, but keeping this, temperature can be increased or decreased depending on the nature of the process. So we have all the three curves. Cyclic process, we have just stated, when you move from A to B, then you come back from B to A, that is cyclic process. So initial and final state would remain same. Change in internal energy would be 0. The net work done during the cyclic process is given by area of the loop. So as you can see, in clockwise fashion, this net work done is area of closed loop for clockwise. This net work done would be positive. For anti-clockwise, this net work done would be negative, but numerically same as that of area of the loop. Find the work done during the circular cyclic process. Now try to understand, is this a clockwise cyclic process? Yes. So what is the net work done? Will it be positive or negative? Positive. And this is equal to what? Area of circular loop. What is area of circle? Pi r square. But here you have two variables. One is pressure, one is volume. Shall I keep it in terms of two variables as R1, R2? What is V2 minus V1? So this is one diameter and half of diameter is the radius, and the other is in terms of pressure. So this is P1 minus P2 This is the diameter by 2, and this is positive. So this is the net expression, and this is your PYQ. This question has been asked in your previous year questions. Any doubt? Manoj has given me the right answer. Now we have next numerical. Heat is supplied at constant pressure to diatomic gas. The part of this heat which goes to increase its internal energy. So increase in internal energy to the heat supplied. This is what you have to find it out. Increase in internal energy is NCV delta T, whereas dQ is NCP delta T. So this is basically CV by Cp, or shall I say 1 by gamma, diatomic gas. For diatomic gas, what is the value of gamma? This is 7 by 5. So in this, so this becomes 5 by 7. So interesting, and this is also one of your PYQ we have. Now, heat engines, a device that converts heat energy to your mechanical work is basically your heat engine. So that transforms your heat partly into work or mechanical energy. This is called an heat engine. The prime components, the hot reservoir, which is usually a source at temperature T1. This is high temperature. So it absorbs some heat, rejects to the cold reservoir, that is usually your surroundings, and work done is Q1 minus Q2, and this is your working substance, which is usually a gas. So it absorbs some heat, rejects part of it, and does some work. Because this is a machine, so we always talk about its efficiency, and efficiency is work done, that is output to the input supplied, and this efficiency can also be written as 1 minus Q2 by Q1, or in terms of temperature 1 minus T2 by T1 we have. So this is interesting. An ideal heat engine, a reversible heat engine that involves no losses, no friction, that is your Carnot heat engine. Carnot heat engine is basically a reversible cyclic process, and it involves 4 steps. So let's suppose initial state of your system is A, pressure, volume and temperature is defined. It absorbs some amount of heat, and the very first stage is your isothermal expansion. So keeping the temperature constant, the system continues to expand with the higher slope, and this is your second stage, that is called adiabatic expansion. So temperature changes to T2. So these are the 2 expansion strokes. So it absorbs, does some expansion isothermally, then does some expansion adiabatically, reaches C, and then starts coming back to the original state, by releasing some energy Q2. So this is isothermal compression stroke, and then finally we have adiabatic compression stroke. The net work done is again area of this loop. So area of this loop defines the net work done, and this is a cyclic process, this is a reversible process, and this is happening in a clockwise fashion. So net work done would definitely be positive, and this is equal to area of this closed loop. Shall we? Now let's work out with one numerical. A Carnot heat engine takes takes, so this is Q1, 3000 kilocalories of heat from a reservoir at, so this is 627, make it to Kelvin, that makes it 900, gives a part of it to sink at 27, so T2 is 300 Kelvin. What is work done? So work done by Q1 is your efficiency, which I can write it down as 1 minus T2 by T1. So 1 minus 300 by 900. So 1 by 3, 1 minus 1 by 3 gives me 2 by 3. So this is W, and this Q1 is 3000 kilocalories. So this 3 goes with this. So work done comes out to be 2000 kilocalories. Now answer is in joules. So we know 1 calorie is equal to 4.2 joules. So when you multiply this, or when you convert it into joules, so that gives me the second option. Any doubt? So let's move to the KTG part, kinetic theory of an ideal gas. So it has few assumptions. What these assumptions are: kinetic theory of gases is based on the molecular picture of matter. So it consists of molecules. So a given amount of gas is mixture of very large number of identical molecules, and this is of the order of Avogadro's number, 10 to the power 23. So this is precisely 6.023 into 10 to the power 23. These molecules are moving randomly in all the directions. At ordinary temperature and pressure, the size of the molecules is very small as compared to the available volume. So there are no interactive forces. It means no interactive forces. There is no concept of potential energy, though they are colliding, but no concept of potential energy. They have only kinetic energy. These collisions are not among themselves. These collisions are with the walls of the container also. These collisions are perfectly elastic in nature and such that momentum and the kinetic energy of the molecules are conserved. So based on this assumption, they exert pressure. So this pressure is 1 by 3 N M into V square. So this is the root mean square. N is number density. So number of particles in a container, that is number of free molecules per unit volume, M V square. So this is the molecular mass also, and PV is equal to this. When you multiply it with 2 and divided by 2, so this is the kinetic energy. So this PV is equal to 2 by 3 times its kinetic energy also. So this is pressure of an ideal gas. And Boyle's law. Boyle's law says for a given mass of an ideal gas at constant temperature, the volume of gas is inversely proportional to its pressure, keeping mass and temperature constant. So this is Boyle's law, and this is the same graph we had just discussed it earlier also during the isothermal condition. So P is inversely proportional to V. This is the same graph, and this is the same graph we had it earlier also. Then Charles' law. So for a given mass of an ideal gas at constant pressure, volume of a gas is directly proportional to its absolute temperature. So with the increase in temperature, volume increases. So definitely this is a straight line graph. It means V1 by T1 is equal to V2 by T2. Now, pressure of a gas is increased 2 times. What should be the change in its volume so that the temperature and number of moles remains constant? So when temperature is constant, amount moles is constant. So PV remains constant as per your Boyle's law. So P1 V1 is equal to P2 V2. Pressure of a gas is increased to 2 times. So if initial pressure is taken as V, the next pressure becomes 2V, V2. So V2 becomes V1 by 2. So change is again V by 2 only. So they are asking about the change. So V2 minus V1, so that is the change, and that is also giving you the same number as V by 2 only. Dalton's law. So when you have good number of gases, the variety of gases or a mixture of gases, but these are non-interactive gases, they are not affecting each other. So then the total pressure exerted by a gaseous mixture is equal to sum of the partial pressure of each component present in the mixture. So let's suppose you have one type of gas that exerts pressure P1. So N1 R T1 by V1. Another gas N2 R T2 by V2. But now keeping under the same conditions, they may have different volumes, but keeping the temperature constant. So Dalton's law says the total pressure exerted by the mixture of these two individual gases is sum of their partial pressures. Then we have law of equipartition of energy. So it says degrees of freedom. What do you mean by degree of freedom? When you allow a gas molecule to show its excitation, how that gas molecule exhibit its excitational energy state, that is called its degree of freedom. So for a monatomic gas, its degree of freedom is 3. So we have 3 translational kinetic energies, X, Y and Z. So these are the 3 coordinate systems along which a single molecule can exhibit. For diatomic gas, the degree of freedom is 5. Out of 5, 3 are kinetic energies and 2 are rotational kinetic energies. So this is how you interpret the degree of freedom. So this is defined as the total number of coordinates or independent quantities required to describe the position and configuration of the system completely. So when you excite a system, how it exhibits its energy state, that is called its degree of freedom. So this is all from today's part. Any doubt, anything, you can please confirm it right now. I am here to answer few of you. So this is all from today's part, Thermodynamics and KTG. Again, this side, Puneet Kathuria, your physics faculty at Aakash. So hope you people have enjoyed the session. See you next time in the next live session. Thank you very much. Thank you.